In mechanics, when you have a question involving a moving object, you may be able to represent the details of its motion on a velocity time graph. That is to say, a graph where the y-axis represents the object's velocity at any given moment, and the x-axis is time as time progresses forwards. As such then, if we were to look at an example like this, we'd be starting down here where the velocity is 0 at time 0. And then, as time goes forwards up until some first time value, this velocity is increasing at a steady rate until you reach v. Here, the line then plateaus, it stays flat, so we're staying at this velocity of v until time 2, at which point the graph then comes down to a 0 velocity again at time 3. Now, instead of just saying it goes up and so forth, we can give a quantity or unit measurement to this gradient. We can say that because you will be working out this gradient by doing the change in v over the change in t, so change in v over t, change in velocity over time, that is acceleration. So, in a velocity time graph, you have gradient equals acceleration. So the steeper a line is going up, the faster the object is accelerating, the shallower, the less it's accelerating. And if it's going down, the steeper, the faster it's decelerating. And shallower, it's decelerating at a slower rate. For this reason, most of the questions that you're going to have with this are going to be to do with constant velocity. Just because it's going to be easier to draw and interpret on a graph, because again, it's a straight line because it's a constant acceleration. If the acceleration was changing, if the gradient was changing, we would have a curve. Another thing that we can do is we can get the area underneath the graph. Conversely, whereas before we did v divided by t to get the gradient, area would be timesing the two axes together, so v times t. Now velocity times time, what does that get you? That gets you displacement. Now if you need a reminder as to what displacement means or how it's different to distance, distance is a total length travelled, but displacement is the strict how far away is the end point from the beginning point, from your start point, in a straight line. With that in mind, you can end up with negative displacement in a velocity time graph if you have a negative velocity, if you end up going back on yourself. Again, velocity is speed, but with a specific direction. So if you started going backwards, your velocity time graph would actually now go into the negative. But regardless of that, what we're saying here is that if you started with a velocity time graph diagram given to you, you could interpret what velocity the object had at a given time, as well as what acceleration it may have been travelling with at that time, or how much distance it has covered, assuming it's, again, gone in a positive direction. Just some other details we may want to consider. If your line is horizontal on a velocity time graph, that means that your velocity is constant, it's not changing. And if your velocity is constant, that means your acceleration is 0. Secondly, if the velocity is 0, we can describe the object, therefore, as being at rest. So if instead of having the diagram first, we have a description first, and it says that at this time the thing is at rest, we know at the very least at that instantaneous point the thing isn't moving. And then thirdly, while most of this is going to be covering velocity time graphs, it should just be made clear that you can also have a displacement time graph, where here the gradient would then equal the velocity, as before. So if velocity divided by time is acceleration, displacement divided by time would give you your velocity. There's nothing for the area of this one. And then if we were just to try to represent this velocity time graph on this displacement time graph, you would end up with some kind of curve, kind of like what you'd have with a cumulative frequency. Because the velocity is starting at 0, but then it's increasing, if the velocity is increasing, the gradient is increasing. So you'd start off curving upwards And then when you get to this level point here, that's a constant velocity, so a constant gradient. And then here, when it decelerates back to 0, because it's just the velocity that's going to 0, it's just the gradient to 0, it would then level off again. Not going to get this sort of thing very often, but just so you're aware, look out on your axes. If it was displacement time, then the gradient will be velocity. Okay. So if we were an example, we would have here that at time 0, this thing already has a velocity. Let's label this velocity u, because if we think back to Suvat, u represents that initial velocity. And then here, let's just call that time 1. The thing, whatever it is, let's just say it's a car, starts to decelerate up down until time 2, at which point we may say is like v1 or something like that. It's the first of the final speeds we could come up with, depending on which part of this we're isolating. The notation is entirely up to you. I'm just using u and v because of Suvat. Once we're at this v1 at time 2, this car then maintains its velocity up until some third time value, at which point it starts accelerating again up until time 4, where it would reach some second final velocity, and then it just levels off once more and carries on as it's going until time 5. If we actually wanted to get some values for this, though, to work out either the acceleration between any given point or the velocities or the displacement, we'll need some numbers for these. So let's just say that this is 5, 8, and 15, and that this could be 4, 6, 16, 19, and 24. If we wanted to work out the accelerations are happening here and here, where we have some steepness to the line. It's not just a flat line. For your accelerations, because we're going to be working out gradient you'll usually do with like difference in y over difference in x. For A1, your 2 points are here. So your y2 would be the 5, and your y1 would be the 8, because that's what you started with, and that's divided by x2 is the 6, and the x1 would be the 4. So this will get you minus 3 over 2 meters per second squared, and yes, it's going to be a negative because we're decelerating and going down. As for the other acceleration, using the same principle, when I'll start here and end here, so your y2 is the 15, minus your y1 of 5, and then that's going to be over the x2 of 19 minus the x1 of 16. This leaves you with your 10 over 3, which again I'm not really going to simplify. Now, if instead we had been asking for the displacement of the entire journey, because we'll be looking to work out the whole area under this graph, we're going to want to split it up into sections. What I might suggest doing in this specific example is to split this up like so. So you have this trapezium here to begin with, like your S1, this big rectangle on the bottom, S2, and then this other trapezium here, S3, although you can split it up in whatever way would make sense for you. For S1, the area of a trapezium is half the sum of the parallel sides times the distance between them. So that'll be half of then this length here is from 0 to 4, so that's just 4, plus, and then this one is just 0 to 6, so that's 6. And then that will be times the distance between here, which is 3. If you work that out, that's going to give you 15 meters. For S2, that's just a rectangle, so we'll just have the base times the height, base of 24 times a height of 5, so that's going to get you 120 meters. And then for your S3, trapezium once again, so it's half. This time the A is going to be between 19 and 24 in the time, so that's going to be 5. And then plus this B here between 16 and 24 is going to be 8. and the height that we're going to times between is then that 10.4. And if we do that, that gets us 65 meters. In total, therefore, if we were just to add all of these up, you end up with a total displacement of 200 meters. So that's how we can use numbers on a graph that is already given to us. How about if instead you were given a description? So we're told that a car takes 120 seconds to travel 2,145 meters. Starting from rest, it accelerates constantly for 30 seconds up to 22 meters per second, where this speed is maintained for t seconds, after which it decelerated constantly to a halt. Sketch the journey and then find the value of t. Well, in this case, we're going to obviously have to start with some axes. We don't know how big they're going to be, so let's just sketch them out like this to start with. For our line, we're obviously going to be starting from rest, so we're going to start from a v of 0, and then we're going to accelerate upwards for 30 seconds until 22 meters per second. We don't know how steep that is on this scale, so let's just draw some straight line going up, and then we'll note that that is at 30 seconds, and on the velocity that's 22 meters per second. At this point, we then maintain this speed as a constant velocity for some other period of time we don't know, but then at the end of that, because it's maintaining the speed 40 seconds, that makes this time 30 add t, not t itself, because we're just adding this t onto the previous time. And then from here, we decelerate constantly to a halt, so that means to a stop. And because we know that this total journey is taking 120 seconds, we'll put 120 there. From here, we can say that the area has to be the 2,145. But other than that, that is the entire velocity time graph as we have information for it. With this then, we are going to find out whatever this value of t is. We're going to use the fact that we know the area and the fact that this is a trapezium. So, like before, area of trapezium, you have half, and then the sum of your A and your B, your parallel sides. This length here is a length of t, because it's constant for t seconds. And then on the bottom here, that base, that B, we're going to add 120 in total. And this is then times by that height of 22. So, if we're now trying to rearrange to get t on its own, if you were to take this 2,145 and divide by the half and divide by 22, that will leave you with 195 equals t plus 120. Therefore, t on its own, if you minus 120, leaves you with 75 seconds. That's the duration for which the vehicle is travelling at a constant speed. Once we have this, we can move on to the second part, which would be that a motorcycle leaves the same spot 10 seconds after the car did. Moving with constant acceleration a, it passes the car at point, capital A, 990 meters from the start, where the car is moving, when the car is moving at 22 meters per second. Find the time that they reach A and then the value of the acceleration A. So, if we're going to draw on the motorcyclist line onto here, just so we might want to visualize, we know that the motorcyclist is leaving 10 seconds later, so their starting point will be at 10, and they're going to then travel at a constant acceleration, so a constant gradient, such that it passes the car when the car is traveling at 22 meters per second. So if I was to draw a line something like this. Now, to be clear, that is not saying that they are passing each other at this point here, where the two lines currently cross. That's just saying that's the moment when they both happen to be travelling at 22 meters per second. If the motorcycle is going to pass the car, having started later, that's going to happen when it's travelling faster than the car, to be able to make up that lacking distance. So really, the time where they cross is going to be somewhere here, and we may use like a lowercase t this time. What we can say, though, is that the area of these shapes are going to be the same as each other because they must have covered the same distance, the same displacement. with this in mind, if we're just trying to find the value of t first, we can actually just focus on the cars graph still. We can say that this distance of 990 must equal the area of that trapezium that makes here. And so once again, we'll just use the exact same formula. So half. Then up here, this distance here, or this time, is going to be t minus 30. And then on the base, that's now just going to be add t, and that will be times by the height of 22. Now, just like we did with the previous example, we'll divide the left-hand side by the half and the 22, so that leaves us with 90 equaling 2t minus 30. Therefore, if you add the 30 over, you get 2t equals 120. Therefore, dividing by 2, t is going to equal 60 seconds. So they pass each other after 60 seconds beyond the car starting. If we're looking for the motorbike's journey, that difference is now going to be 50 between the 10 and the 60. With this information, we can now work out the missing dimensions of the motorbike's graph, because to be clear right now, we have no idea what its v is, and only by knowing the change in the velocity over this known time can we work out this acceleration. This now is a triangle rather than a trapezium, so we're just going to be looking at half base times height. And we know that that distance, that area, is once again this 990, because they're travelling the same distance as each other. So 990 equals half times 50 times v. So just dividing the 990 by half and then by 50, that leaves you with v being 39.6 meters per second. From here, therefore, if we just want our acceleration, the difference in the y's, or the difference in the v's, so your 39.6 minus 0 where it started, over that difference here, which we've already identified, that difference is just 50. This then gives you an acceleration of 0.792 meters per second squared. So if we're all right with that, we can see how we've taken these wordy descriptions and used them to create velocity time graphs with which we can create equations that allow us to solve for missing information. Let's just see how you'd get along with an example of your own. So, a particle initially moving at 5 u-meters per second decelerates uniformly for 6 seconds, reducing its speed to 2 u-meters per second. It maintains this speed for 16 seconds before decelerating to rest in a further 2 seconds. Sketch the velocity time graph, finding expressions for each deceleration in terms of u, and, given then that the total distance is actually 200 meters, find the value of u. Think about how we've been constructing the velocity time graphs so far, and then how we can use different measurements of distance, speed, and acceleration and time to get out the different sections, and how we can then interpret them. Think about how you do this, pause the video, have a go for yourself, and then press play again when you're ready to compare. Okay, so to start off with, again, we just want to sketch out some quick axes to begin with, just your v against t. Now, initially, we're moving at 5 u-meters per second. We don't know exactly what that's going to be, so let's just put that here on our axes. Then, because it's initially moving at this, and then we're decelerating, we're going to interpret that as it just decelerates straight away. We have no other time frame anyway for how long before it would start decelerating. So straight away, we're now going to decelerate for 6 seconds until you reach this point of 2u. This is then kept as a constant speed for a further 16 seconds. So that brings us down here to 22. And then finally, this decelerates to rest here at what would be 24 in a further 2 seconds. This here is our sketch using the information that we have. And then from this, we're wanting to find expressions for each deceleration. Well, the acceleration or decelerations are the same thing, just deceleration is specifically negative. They're happening at these slopes here, so they're A1 and A2. Like before, when getting these accelerations, these gradients, we'll just be doing the difference in y over the difference in x. Difference in y here, the y2 is the 2u, and the y1 is the 5u, and then this will be over an x2 of 6 and an x1 of 0. Together, this therefore makes minus 3u over 6, which is the same as minus a half u. As for the other deceleration, once again, difference in y over difference in x, the y2 in this case is now 0, and the y1 is now the 2u, and this will be over your x2 of 24 minus x1 of 22. So this is the same as minus 2u over 2, which is just the same as minus u. And finally, to work out the value of u based on the fact that the distance is 200, how can we use knowledge of the distance? We can say that it's the area under the curve, or under the graph. In this case, we could split this up in a few different ways. You could make this a upended trapezium here, and this a usual trapezium here. What I'm probably actually going to do in this case is actually just split it up into two triangles and a rectangle, just whichever works for you. For this first triangle here, what we're going to have is half base times height. So half times a base of 6 times a height of 3u. Together, that's going to get us 9u. For the rectangle, well, that's just base times height. So the base is 22 and the height is 2u. So together, that makes 44u. And then this triangle here, once again, is going to half base times height. Half times a base of 2 times a height of 2u, which gives us, adding these all together, you get 55u equals that 200 meters total distance. So divided by 55, you end up with u being this 4 meters per second. If you're happy with that, let's just move on to just see one other way of having this question, or one other way of how these graphs can look. A ball of mass 0.3 kilograms is released from rest at a point which is 2 meters above horizontal ground. The ball moves freely under gravity. After striking the ground, the ball rebounds vertically and rises to a maximum height of 1.5 meters above the ground, before falling again to the ground. The ball is modelled as a particle. Sketch in the space provided of the velocity time graph for the motion of the ball from the instant when it is released until the instant when it strikes the ground for the second time. Now, within the description of this question, we have a number of details that we usually wouldn't need, such as the mass. This will be because this has come from a larger question, and we're just isolating the velocity time graph section here. For this, what I'm going to do, when I sketch out my axes to begin with, what I'm actually going to do is I'm going to put my x-axis, my time axis, in the middle, having this section that goes below. The reason for this is, again, going back to that definition of velocity, it's speed in a given direction. So that means that if we take one direction as positive, and then the object starts travelling in the reverse direction, that is now a negative velocity. Here, because this ball is released from rest, it's going to hit the ground, and then it's going to bounce up and come back down again. It's going up and down, its direction is changing. We are going to have a part of this graph which is in the negative. So, we're starting from a point which is 2 meters above the ground, and we're starting from rest. So we're going to be starting from this 0 here. When you have questions where things are moving vertically, as we've had with Suvat under gravity, you need to decide whether up or down is going to be positive. It doesn't ultimately make a distance so long as you acknowledge which is which and you keep this consistent. What I'm personally going to do is I'm going to say that up is positive. Therefore, when this ball is initially dropped, that means it's travelling down, it's travelling in the negative. So from this initial 0, When we are now starting to fall freely into gravity, because gravity is a constant acceleration and freely means we don't have to worry about any other forces impacting it, we're going to have a constant acceleration into the negative, getting faster and faster. We don't know exactly what these values are going to be. They presumably would come from the other parts of this question, but you end up reaching this first v value here at some first time, such that the area of this triangle here would be 2. Now, the reason why we stop here is because this is where the ball has now reached its greatest negative velocity, but it then hits the ground. We're going to assume this is an instantaneous switch, that it goes from heading in a downwards direction to an upwards direction with an almost equal velocity just in the positive direction. It's not going to be exactly equal because some energy will be lost to the ground, and we know as well it's not the same amount of energy because it doesn't reach its original height. It only reaches 1.5 meters. So how this is going to look here is this line is then going to jump up into the positive to some value where we have v2, and just to be clear, so this distance here should be slightly less than this distance here. Now that the ball is travelling upwards at a high velocity, we're now going to be in this region, but as it travels upwards, it's now going to be slowing down again. If it wasn't slowing down, then it would keep on travelling upwards infinitely. So the line is going to come downwards, and again, it's going to come down at the same gradient as this line from here, because again, it's only moving under gravity. Gravity is the only constant acceleration. Even though the line is coming down here, we're still travelling upwards. We're still in the positive region, it's just we're slowing down. This point here, this second time that we may wish to note, that is when the ball is at its greatest height. In that moment, it is instantaneously at rest again. It's not moving up, it's not moving down, nor is it really moving left and right. When we do this kind of quick sketch as I did on the right here, we spread it out as if it's going left to right, but really it should just be going up and down on top of itself. Here then, we now start to fall, still under the same acceleration, so it's still going to be the same gradient, but now we're back in the negative region because we're now heading down to the ground again. So this line is going to continue here, and you should end up at some value here where this third v value, from that to 0, this should be the same as your, of the same distance away from 0 as your v2. So yeah, to be clear, so v1 is going to be greater than v2, just obviously in the opposite signs, and v2 should equal v3, just in opposite signs. Because yeah, it's going to have come back down with the exact same energy, the exact same velocity, because we're assuming there's no like air resistance it could have lost anything to. This then hits the ground, so we then just go up to back to a baseline, because there's an instant now where it's kind of nebulously still hitting the ground, but it's 0, and it's about to go back up again if we had allowed the model to continue. So this is what we can get if we have something that's moving up and down, or indeed left and right. Well, usually specifically in a bouncing up and down, because we are going to assume in this case that because when it's falling, it's not going to be decelerating. It's not going to slow down as it falls. It's going to be getting faster. So it's not going to reduce itself to 0. It's going to hit the ground with some notable velocity. And it's then just in that moment, this notable velocity switches in the other direction. So with a dotted line, we now have to jump up into the other region of the axes. Hopefully that's clear. This is kind of like a peculiar form of the velocity time graph, just a quirk that can happen when we have this thing bouncing up and down. Usually you would just have your usual like trapeziums and triangles and rectangles that we saw above. Either way, it's all down to the same concepts. It's just a matter of interpreting the scenario.